Hello everyone. Today we will discuss about the Legendre transformation. So let us see what is Legendre transformation and what is the application of it in the thermodynamics. So if you would like to draw a line, so what information is required? Suppose I have xy axis and I would like to draw a line. So I require the 2 points, that is x1 y1 and x2 y2. Let's say here. So I can draw a line with the help of this. The same line I can draw if I know the value of dy by dx, and that is called slope m and the intersection point C. So I can draw this line with the use of y is equal to mx plus c with the known values of x1 y1 and x2 y2, or with the known values of m and c. So here no information I am losing because I am representing the same thing. Only the way of representation is changed. And this equation, this line of equation is given by y is equal to mx plus c, where y is dependent variable and x is independent variable, and m and c are the constant. If I rearrange this equation, so I can write c is equal to y minus mx. So I am representing the same line of equation in another way. So my notification or my calling is different, but I am not losing any information. So what happening here is, now I have replaced my variable y to the x and another y to the c and x to the m. So with the known value of m and c, I can draw the line, or with the known value of x and y, I can draw the same line. This is called the Legendre transformation. So here I will change m is nothing but the dy by dx. Let's see one example for the enthalpy formation, and we will clear that how it is functioning. So for this, we know that the internal energy E U is a function of S, V and N, where S is entropy, V is volume, U is internal energy, N is the number of components. So I will replace this, I would like to replace this variable volume with their corresponding variable P, or thermodynamic property P. And for this, I will replace this C with the another notation, that is H. So we can write H is now in a function of minus P. So I am replacing what? In place of y, my y is u and x is what? V. I would like to replace m, and m is nothing but the dy by dx. So m is nothing but the dy by dx. It means that it is du by dou v. So dou u by dou v, where s and n are constant. This I can replace with another term minus p. How this minus p is come? We know the equation du is equal to, this is for x axis, this is for y axis. So du is equal to TdS minus PdV. Okay. Du is equal to TdS minus PdV. How this comes? This is outcomes of the combination of first, second and third law of thermodynamics. So here I will divide V in a both side, keeping entropy constant. So this term will goes to 0 because entropy is constant, and here dou V by dou V, this goes to 1. So what will be remaining? It is minus P. So we can see here minus P we can replace with the M. Now coming back to our Legendre transformation, transformation. So y is equal to mx plus c, and I am changing c is equal to y minus mx, and c is nothing but the h, and y is u, m is minus p, and x is v. This I can write u plus pv, and we all know that the enthalpy is a summation of internal energy and multiplication of pressure and volume. So here we can see h is a function of uh, h is a function of u plus pv, or if I will put this, or I will differentiate this with respect to I will differentiate both sides, so I can write dh is equal to du plus pdv plus vdp. I could replace here. So this term I can write dh is equal to du plus pdv plus vdp. Now du is equal to, earlier we know that du is equal to tds minus pdv. So let's write here dh is equal to tds minus pdv plus vdp, and this plus pdv, and this both will be cancelled, and tds plus vdp, and hence we can write h is a function of sp, and if number of component is there, so sp and n. So finally we can say that we are changing the information from sv and n to sp and n with the new notation, and we call it enthalpy. So enthalpy is nothing but the function of sp and n. So here we are not losing any information. The only thing that we can see is this is the energy, but this energy is now represented in the form of enthalpy. So where pressure is the variable, we call that energy as enthalpy. So just we have seen that the application of Legendre transformation for the formation of enthalpy. Now we will see the same for Helmholtz free energy. So we will see the Helmholtz free energy, that is represented by the A. So for this formation of Helmholtz free energy, we will replace variable, that is entropy, with is the corresponding properties, that is the temperature. So once again, here y is our u and x is what, s, and what will be the m, dy by dx. So we will use the our reference equation for internal energy, that is du is equal to tds minus pdv. Now what we want, our properties variable is entropy, which we will try to replace. So here it is come dou y by dou x is dou u by dou s, where volume and n constant. So here I will divide both sides by dou s and keeping volume constant. So this term goes to 0 because volume is constant here and here volume is 0, and this term goes to 1. So dou u by dou s is volume constant, is nothing but the t. So here I can write t. So our the property variable m is nothing but the t. Now we will go to the actual equation y is equal to mx plus c, and our transformation equation is y minus mx, and we will put the variable. So y is what? Y is u, and m is what? T, and x is what? S. So this comes, and c is what? A. So A is equal to u minus ts. Let's differentiate both sides. So dA is equal to du minus tds minus sdt. Once again we know that du is equal to tds minus pdv. So we put it here, TdS minus PdV minus TdS minus SdT. So TdS will be cancelled and the term remaining is minus PdV minus SdT. Let's rearrange it. So minus SdT minus PdV, that is what is dA, or we can see that A is a function of T and V. T, V and if N is there then N. So here we can see the same energy representation when I am change this non-measurable property, because entropy we cannot measure directly. So this entropy is measured in the form of temperature, and when I change this property, so that energy is called the Helmholtz free energy. So when we change this entropy in the form of temperature, and that energy we measure is called the Helmholtz free energy. So this is the another application of Legendre transformation to determine the Helmholtz free energy. The same manner we can go, and when we replace these two variables simultaneously, entropy with its corresponding variable temperature and volume with its corresponding variable pressure, we will get the another set of energy equation, and that is known as the Gibbs free energy. So we will see the same. Now we will see the Legendre transformation of internal energy to get or develop the relation for Gibbs free energy. So in this case, in the previous example, in the previous elaboration, we have changed only one variable at a time, like volume in place of uh, pressure, and temperature in place of entropy. So this time I will change both variables simultaneously and we will get the same thing. So here uh, our relation was y is equal to mx plus c, but here I have two variables, so I will write y is equal to m1 x1 plus m2 x2 plus c, and therefore m1 is nothing but dy by dx1 and m2 is nothing but dy by dx2. So in this case x1 is s and x2 is v. So dy by dx1 is m1 and m1 is equal to dy by dx1 and therefore du by ds. So when dou by dou s we will write the v and n will be constant, and for another slope m2, dy by dx2 we will write dou u by dou v, where s and n will be constant. So from the earlier we have seen dou u by dou s, that is replaced by the properties, another property, that is t, and dou u by dou v, that is replaced with the properties minus p. So let's put to the equation and convert this into the Legendre transformation. C is equal to y minus m1 x1 minus m2 x2. So C is what? C is another symbol I am giving, that is the G, and Y is U, M is M1, M1 is T, so T, and X1 is S, minus M2, M2 is minus P, and X2 is V. So we can see here U minus TS plus PV, or U plus PV we can write H minus TS. So the Gibbs energy is nothing but the difference of enthalpy and multiplication of temperature and entropy. When I will differentiate both sides, so dG is equal to dH minus TdS minus SdT, and dH, dH is equal to, we just develop that, or if you want we can put it here itself, dH is equal to uh, du du plus pdv, or we know that dH is equal to tds plus vdp. So we can write here tds plus vdp minus tds minus sdt. TDS will be cancelled. I will put it here in front. So SDT plus VDP dG is equal to, or we can see that G is a function of temperature, pressure, and if number of most components were there, so Tp and N. So now you can see that the function variables SV and N is replaced with the another variable, that is Tp and this I am representing with the another symbol that we call the another symbol G, and that we call the Gibbs free energy. So Gibbs free energy is a function of temperature, pressure, and number of components. So this is the completely formation of use the Legendre transformation of another form of energy, or that is actually the energy which we are measuring, which we are finding with the measurable properties. So G is a function of Tp and N, like we have just seen. A was a function of Tv and N, and H was a function of what, S P and N. So this is the, by the use of Legendre transformation and this function internal energy, we can get enthalpy, Helmholtz free energy, and Gibbs free energy. Or we can see du is equal to the basic equation, du is equal to TdS minus PdV, dH is equal to TdS plus VdV, and dA is equal to minus SDT uh, minus SDT minus PdV, and dg is equal to minus SDT plus VdP. So minus SDT plus VdP. Or we simply see these four relations, du is equal to TdS minus PdV, and when I will replace at the very beginning in the Legendre transformation, I have replaced that variable V, extensive properties, with the another intensive properties, pressure. So now when I have replaced this one, and when I will replace this variable, I am putting positive symbol here, means negative symbol is changed. So it is that energy is the form of enthalpy. Similarly, we refer back the equation 1, and this term temperature and entropy I have replaced, entropy and temperature, and when I will replace, the symbol will be changed. So minus SDT minus PdV, and this relation is called free energy. The same manner, in this equation 1 I have replaced the both variable, I got this and Gibbs free energy. So this is, my conclusion is that this all four relations is the energy representation, but energy is measuring with the different variables, and due to that different variables we call these are different by the different names, but these all are energy only. So when we measure the change in energy either in terms of volume, basically we consider internal energy. When pressure and entropy, our focus parameters, we call it enthalpy. If temperature and volume is there, we call it Helmholtz free energy, and temperature and pressure is there, we call it Gibbs free energy. So this is the completely application of the Legendre transformation. So we can see here all these four relations, these all are energy only. The only things difference is in this all is the measuring variables or the dependent variables. So this we have characterized for our help, and to categorize the things, to measure how what are the measuring properties, and this is the application of Legendre transformation. And we will see the application of this Legendre transformation for some existing relation as well. We will see the application of Legendre transformation of this given relation and this relation we will transform to the Gibbs energy representation. So we know that this is the, for Gibbs energy representation, we will change two variables simultaneously, and those variables are S and V, and in this given relation the K is arbitrary constant and N is also constant. So we will replace the entropy and volume with their respective thermodynamic property, and we will develop the another relation for the Gibbs free energy. So for Legendre transformation, we know that the mx plus c, this we will convert to the c minus c is equal to y minus mx, and for multivariables, because this gives energy representation, this relation we will write m1 x1 plus m2 x2 plus c, and here m1 x1 minus m2 x2. So here y is u and x1 is s and x2 is v. So m1 is equal to dou u by dou s, keeping volume constant, and this is nothing but the T, and m2 is equal to dou u by, variable is volume, so dou v, keeping entropy, and this is nothing but the P. So here I will put the value of m1 and m2, x1 and x2 and y, and this c constant I will replace with the Gibbs energy term that is given by the capital G, and we will see what comes. So G I will put in place of C I will put G, y is equal to u, and m1 is nothing but the T and x1 is s, then minus m2 is minus p, so I will put minus p here, and x2 is v. So this relation is comes u minus ts plus pv. So u is equal to, it is given k is q by vn minus t s plus pv. This is the relation for Gibbs free energy, but still this relation is not completed. Why? Because when we transform this from internal energy to Gibbs free energy, the variable S and V have to be eliminated. So this S and V we have to be eliminated, and when we put the value of S and V in this equation, we will get the relation, the correct relation for the Gibbs free energy representation. So how to get the value of S and V? We will get the value of S and V from this differential term. So what to do is, we know that T is equal to, from here, dou u by dou s, V is constant. So the relation for u is given here. So I will differentiate this relation for entropy, keeping volume K and N constant. So this term will come 3k s square by Vn. 3k s square by Vn. So here I can see that you can see that T and S are here, and this equation we will rearrange. So we can write S square is equal to TVn by 3k, or S is equal to T, better you write in this way, T to the power 1 by 2, V to the power 1 by 2, N to the power 1 by 2, 3 to the power 1 by 2, and K to the power 1 by 2. So this entropy now we can put here, and the relation will be rearranged. Similarly, we know that from equation number this, minus P is equal to, let it be like little bit down, so minus P here is equal to dou u by dou v s. So differentiating this relation, keeping k, s and n constant, v will be differentiate. So this will become k s cube by n dou by dou v 1 by v. By solving this, we will get ks cube by n v square, and because this is in denominator, the minus symbol will become here. So here we have the relation of minus p ks cube by nv square. So this v I have to eliminate also. So let's change this, rearrange this relation for the v, and we will see both side is minus, so minus minus will be cancelled, and v square I can write, I will see v square here and p will be here. So ks cube by np, ks cube by np. But we know that from this relation, entropy in the form of temperature, volume, and either I have to eliminate V here also, because when we put this entropy over here, so V will be also exist. So we have to rearrange this both equation in the form of that, like S in the form of temperature, number of components, and variable constant K, and similarly the relation for V in the form of temperature, volume, temperature, and K. So let's put the value of S cube here from this above equation and see the find the relation of V square. So V square is equal to K upon np, and this is the s cube and this is the relation. So I can write t to the power 1 by 2, v to the power 1 by 2, n to the power 1 by 2 divided by 3 to the power 1 by 2 and k to the power 1 by 2 and whole term cube. So let's solving here. I will get k t to the power 3 by 2, v to the power 3 by 2, n to the power 3 by 2 divided by n p into 3 to the power 3 by 2 and k to the power 3 by 2. Let's see what will be cancelled here. So k is here, k to the power k and k to the power 3 by 2. So let's solve k first. So this will become, so it will be minus 1. So k to the power 1 by 2. Let's took another term part here. So t in denominator no t, so t to the power 3 by 2, v to the power 3 by 2 is still there, then n to the power 3 by 2 in numerator and denominator n, so n to the power 1 by 2, numerator is now rearranged, p is there, denominator, and 3 to the power 3 by 2. So this is the value of v square. So v square is here and v to the power 3 by 2 is here. So what to do is just simply rearrange of this v, I will shift here. So v square minus 3 by 2 is equal to t to the power 3 by 2 n to the power 3 by 2 1 by 2 upon p 3 to the power 3 by 2 and k to the power 1 by 2. I simply shift this to the left hand side, and this will become v to the power 1 by 2 is equal to t to the power 3 by 2 n to the power 1 by 2 upon 3 to the power 3 by 2 p and k to the power 1 by 2. Shift this power over right hand side, so we will find v is equal to, or let's put the square in both sides. So v is equal to t cube n upon 3 cube p square k. So this is the relation for v in the form of t and pk. This relation, this I will put over here, or this I will put over here. So I will get the relation of t and k for the entropy as well. So let's use S is equal to what given here is T to the power 1 by 2, just writing, and N to the power 1 by 2 upon 3 to the power 1 by 2 and K to the power 1 by 2. So here V to the power 1 by 2 is given. So, and this was the relation V to the power 1 by 2 is equal to T to the power 3 by 2, N to the power 1 by 2 upon these terms. So let's put over here, the term will come T to the power 3 by 2. The mind it, this I was keep square in both sides. So I am keeping inner side values. So T to the power 3 by 2, N to the power 1 by 2, 3 to the power 3 by 2 P, and K to the power 1 by 2. By solving of this, what we will get? T to the power 1 by 2 and T to the power 3 by 2. So 1 by 2 plus 3 by 2 is 4 by 2, means square. So T square, N to the power 1 by 2 and another N to the power 1 by 2 is N. 3 to the power 1 by 2 and 3 to the power 3 by 2, once again 3 square. K to the power 1 by 2, K to the power 1 by 2 is K and P. So we can see here, now S is also comes in the form of T and Kp, and here we got V is in the form of T and P and K. So now we put the value of this 2 over here, this relation, and see what's come. So G is equal to, now K by V, K by V, S cube by V I have to put. So S cube is T square N by 3 square K P. Let me write it proper way. 3 square. This is what? This is the cube upon V. V is what? T cube N. So T cube N upon 3 square P square K minus T into S. S is once again T square N upon 3 square Kp and plus Pv. So plus P into V. V is what? T cube N upon 3 cube P square K. So this is the relation, sorry, here that N will become in place of V. So this is the relation. By solving this, we will get the another relation. We will come to the our final. I hope this part is over. So let me erase this part. We will get some more space to work out in. So G. Let's see what come. First we will change this denominator terms to the numerator and rearrange this term. So K by, there are two ways to solve such type of problems. Either by our own calculation we simply cut, or we just elaborate it and then cut later on. So if we have much confidence, so we can simply cut by ourselves, and if you do not have much confidence, then let's elaborate the terms and then you cancel. That is the easiest way to reach the correct solution. So I will elaborate here, expand it here. So t square and cube, so t to the power 6 n cube upon 3 square and cube, So 3 to the power 6 k cube and p cube. This term, now denominator term, so this the bottom part will be goes upper side, so 3 square p square k upon t cube n. T cube and now here this is simple t cube n upon 3 square kp, then plus once again t cube n, denominator, in denominator you can see there is a p square and here is a p, so p will become 3 cube p k. Let's check what will be cancelled here. We start with the k square, then t to the power 6, then n cube p square and p square. Denominator n, so n square 3 to the power 6 k cube p cube t cube, and we already considered minus t cube n upon 3 square kp plus t cube n upon 3 cube pk or kp, right in a one sequence, so it will be easy to solve. This is very long, but now it's very easy, we can cancel it. तो अभी अब हम इसको फिर से सॉर्ट आउट करते हैं। यहाँ पर देखिए तीनों में टी क्यूब एन बाई पी के कॉमन है और 3 स्क्वायर भी हम ले सकते हैं। सो टी क्यूब एन बाई 3 स्क्वायर पी के बाहर ले लूँगा तो यहाँ पे क्या बच जाएगा 1/3 माइनस यहाँ पर हो जाएगा 1 और यहाँ पर बच जाएगा फिर से 1/3। तो टी क्यूब एन बाई 3 स्क्वायर पी के, और जब हम इसको सॉल्व करेंगे तो ये हो जाएगा 1 माइनस 3 प्लस 1 अपॉन 3 और ये हो जाएगा माइनस, देयरफॉर हम इसको नीचे ले लेते हैं, इसका काम हो गया है, इसको हटा ले। तो माइनस बाहर आ जाएगा 1 प्लस 1 2 माइनस 3 मीन्स माइनस 1, तो माइनस बाहर आ जाएगा टी क्यूब एन बाई डिनोमिनेटर में 3 है और यहाँ पर 3 स्क्वायर है, तो 9 इंटू 3 27 पी के। दिस इज द फाइनल फॉर्मूला ऑफ द final representation in the form of Gibbs energy of the given relation, and we can see here G is now function of T and P. So G is a function of T and P or T, P and N. So this is the final Legendre transformation for Gibbs energy of the given relation, which was given in the form of internal energy. There is a another is inverse Legendre transformation. अभी तक हम क्या देख रहे हैं, अभी तक हम ये देख रहे हैं कि हम फॉरवर्ड डायरेक्शन में जा रहे हैं और हम एक नए रिलेशन के रूप में आ रहे हैं। यदि हम इसको ट्रांसफॉर्म करें, when we reverse this or take the inverse of this, so this relation should be come to the here. So that we will see in the next class. Okay, so thanks for watching till now. Next class we will see the inverse Legendre transformation.